Okay, welcome students to video class 41, and in this video we'll start with the state model of a continuous time system. Now by state model it refers to the representation or the description of a system uh, of this continuous time system. Now, as I've mentioned in the previous video, that a state model, it's a mathematical description, and a state model will be having a state equation and this output equation. By these two equations, we can describe the system completely so that you can evaluate the performance of the system. Okay, basically this, as I've mentioned in the earlier video, that the state space variable is another method by which you perform analysis, just as we have done with the transfer function of a system. Okay, again you are to consider a system like this, which we have seen already. I'm going to have a recap of that. Assume that you are giving an input and I'm designating that by the letter U, U1, U2 up to UM, meaning you have M inputs, and which gives you an output y1 of t up to yp of t, meaning you have p outputs. Okay, now along with this you have the inherent, the system has got the internal states, or the that represents the states or initial conditions, or whatever you can call. So these are all the inherent things, okay, or we will be calling this as the state variables, okay, or it gives you an information about the past. Okay, so as I've told you earlier, that if you consider an electrical system with a capacitor, even if you are not giving this input, this particular system may have a capacitor voltage. So that capacitor voltage can be a state variable, which also determines the output. Okay, so if you are not considering this, we will we can see that this output only depends on the input. But practically speaking, if you have a capacitive element or an inductive element in an electrical system, then this result may go wrong if you are not considering the state variables. So that is the meaning of this, introducing the state variables, and you are considering you're having n state variables. Okay, now the number of state variables actually depends on the system. Okay, so that you will understand later. So since there are n state variables, and the variables are defined as x1 of t, x2 of t up to xn of t. Okay, right? Okay, now state model gives you the description of the system, or it is rather a mathematical description. Or the state model consists of two equations. One is called as a state equation, right? State equation, and other one is called as the output equation. Okay, now these two combinedly describes the system. Okay, so any system can be described by this, a be it a linear system or a non-linear system. They can be represented, or they can be described by these set of equations called as the state equations and the output equation, right? Okay, now let us see what is the state equation. We already know, we have studied in the first module. See, an electrical system or a mechanical system can be described by an nth order differential equation. Okay, nth order differential equation of the form, say d raised to y of t by d raised to n of dt raised to n plus say some a1 into dn minus 1 y of t by dt raised to n minus 1, etc., is equal to say some f of t, and so on. So this is an nth order differential equation which describes a system. Okay, now this nth order differential equation, what does the state equation refers to is, state equation is a set of first order differential equation. First order differential equation. What I meant is, if you have an nth order differential equation which represents a system, you can break it into n first order differential equations. Okay, and this n first order differential equations, the set of this n first order differential equations are called as the state equations. So in a sense, you can say that for a system having an nth order differential equation, there will be how many equations? You will be having n state equation. For example, if you consider a differential equation of the form d square by dt square plus say some 2 into y of dy of t by dt plus 3 y of t is equal to say some f of t or x of t, whatever it is. Now this is a second order differential equation. Now how many state equations this will be having? This will be having 2 state equations. Okay, that's what I meant. So that means this can be, so you don't have to worry how you will be decomposing it into first order. This can be decomposed into 2 first order differential equations, and this set of equations are called as the state equations of the system described by this differential equation. So that is the logic behind this. So how will you obtain the state equation? The state equation is obtained by the nth order differential equation that by which that system is described. Okay, and that the logic is you will be decomposing that into the first order differential sets of first order differential equations, and they are called as the state equations. Okay, right? Okay, so similarly, if you have a third order equation, say of the form d cube by of this form, okay, etc., is equal to some f of t, this can be decomposed into 3 first order differential equations. So such a system will be having 3 state equations. Okay, right? And it goes on like that. So if you go in this line, if you have an nth order differential equation, then you will be having n first order differential equations. Those equations are called as the state equations. Okay, now I'm going to give you some examples by which to show you how to decompose an nth order differential equation. Say, let us first of all consider an example of a second order system. Okay, of a second order system whose second order equation is given by, say for example, d square y of t by dt square plus a1 into dy of t by dt, okay, plus a0 is equal to, say, the input, because I'm using the exactly the same notation as I have used in this block diagram, but the difference is this is a single input. So I'm just giving you an example of a single input single output system, while this one is a multiple input and multiple output system. Now whatever we learn from this, that will be just applied on to this. That's enough. So we'll be starting from the simple SISO, or the simple input simple output system. So anyway, there is nothing to explain about this. Y of t is actually the output. Okay, y of t is the output and u of t is the input, right? Now or it is actually the response when you give the u of t. Okay, now we are going to see how you can decompose it into a differential equation, into a single order differential equation. This is a0 into y of t. Okay, now in this y of t, we know that this y of t is the single output. Now I can assign that y of t to be one of the state variables. So I am calling that state variable as x1 of t. Okay, so say for example, if in your say in an RLC circuit, if you give a voltage, right, so there will be a current I of t. This I of t is actually the response. So instead of I of t, you have I of t here. This is the response due to this input. So you can call this as the one of the state, y of t as x1 of t. Now if y of t is assumed to be x1 of t, right, x1 of t refers to one of the states of the system. So this y of t is equal to x1 of t. Now if that is the case, then you have a dy of t by dt, right? So dy of t by dt is actually equal to x1 of t dot, right? So x1 of t is actually equal to dy of t by dt, right? So I am putting that in a box, right? Okay, I'm putting that in a box. Now coming to this side, you have a double derivative. Now what is this d square y of t by dt square? D square y of t by dt square is nothing but it is x1 of t double dot, right? x1 of t double dot, right? Now if I can assign this to b, that is the first derivative of the state. This is the system state, one of the states, x1 of t as one of the states, okay, and of the state variable. I am assigning this x1, the derivative of this state variable as another variable, right? So I'm assigning it to be x2 of t. That is, for example, in this case, I have assigned I of t to be x1 of t, and x2 of t will be assigned as the derivative of I of t. That's it. Okay, so this is another variable, right? Now so this is a state, so this is x2 of t. Now this is actually equal to what? Equal to x2 dot of t, right? This is x2 dot of t is actually x1 of t double dot, right? Now isn't it? So this is x2 of t, and x1 of t double dot means x2 of t single dot. It is as if you take the derivative of this, right? That is dx of x2 of t. So now substituting in this equation all these things which we have just seen, say d square y of t by dt square can be represented as x2 of t dot plus a1 into dy of t by dt, and that is nothing but that is equal to x2 of t, right? Then plus a0 into y of t. What is that y of t? Y of t is again x1 of t is equal to u of t, or you can call this x2 of t dot is equal to minus a1 minus a1 x2 of t minus a0 x1 of t plus u of t, right? So I'm also putting this again in a block, okay, right? So these are the two equations, the two first order derivatives, right? Look at this. This second order equation has been decomposed into two first order equations, right? One in the form of x1 of t, which is assigned to be another state variable, x2 of t, and you find out the derivative of that, and you will be getting this. So look at this. This is let us study something from this. This is a second order system, and we have assigned two state variables, x1 of t and x2 of t, meaning the number of state variables will be equal to the number of the order of the system, right? And not only that, these first order equations, these are first order differential equations, x1 of t dot, single dot, that is first order derivative. This is also the first order derivative of the second variable which we have assigned. So these first order derivatives equations called as, these equations are called as what? These equations are called as the state equations. State equations of the represented by this nth order differential equation. So how many state equations you have for a second order system? You will be having two equations. One is x1 dot of t is equal to x2 of t. Okay, you can extend this block, right? You must write like this: x1 of t is equal to x2 of t, while x2 dot of t is equal to minus a1 into x2 of t minus a0 x1 of t plus u of t, right? Now, another thing that you can find out is, so when you write down the state equation, so the derivative or the state equation is the equation of the set of first order equation. Now when you look at the state equation, you can see that it is a combination of some weighted sum of the state variables. It is the combination of the weighted sum of the state variables and the inputs, right? Okay, now if you can extend this to a multiple input system, you can say that this there will be, so this is having an n state variable, meaning you will be having n state equations, and each equation will be a function of what? Function of the derivative, the first order equation corresponding to this system or corresponding this state variable will be a function of the state variable as well as the input. Okay, right? In this case, it is depending on the n state variables and m inputs. Now I'll show you one more example how to decompose it into how to decompose a nth order system to a single order system. Okay. Okay, now these are the two equations. I'm calling this as equation 1 and equation 2. I can directly convert it into what? Into the matrix form as, say, this will be x1 dot of t and x2 dot of t, right? So this is x1 dot and x2 dot. So this is the first derivative of the state variables. That will be equal to what? Equal to that will be equal to, you can see that x2 of t is equal to x1 of t is equal to x2 of t. So that will be you will be having x1 of t and x2 of t. So x1 dot t is, you have only x2 of t, no x1 of t. That means this will be 1 and this is 0, right? Right, that is what this equation says. Now what about this? This will be minus a1, right? Minus a1, minus a0. This is minus a0 and minus a1, right? So this is the equation. This is called as a state equation, and it is not complete, right? That into here also it is plus 0 into input. Here there is 1 into input, right? So you can say it as u of t into 0 and 1, right? Okay, 0 and 1 u of t. Okay, right? Okay, so there is a correction. This must be a column matrix with 0 and 1. Now when you write the equation from this matrix, x1 of t is equal to 0 into x1 of t plus 1 into x2 of t plus what? Plus 0 into u of t. Okay, now okay, so this is actually the matrix equation, or this is the matrix form of the state equation. Now I'll give you one more example. Say, for example, if you start with another differential equation of a third order, tq plus a2 d square y of t by dt square plus a1 dy of t by dt plus a0 into y of t is equal to u of t. If this is the case, you can start again assigning y of t to be equal to the first state variable, that is x1 of t. Now you can also have a derivative of this, that is dy of t by dt is actually equal to x1 dot t, right? And that you can assign as the second state variable, and you can have d square y of t by dt square, and that is nothing but it is x1 of t double dot, or that will be x2 of t single dot, and that you can assign to be another state variable x3 of t. Okay, right? So when it reaches the third state variable, you have altogether three variables, and we have already seen that there is a correlation between the number of state variables and the order. So it has reached the maximum limit. Now you can write down this, substituting here, you will get this as, this is d square y of t. So what must be d cube y of t cube? So that will be x3 of t dot, right? When you take the derivative, it becomes d cube, right? So this is x3 of t is equal to, okay, bringing this, okay, this is a0 into x1 of t minus a0 into x1 of t minus a1 into dy of t. Instead of dy of t, you can write this as x2 of t, right? So plus minus a2 into x3 of t, right? Now that plus u of t, right? So you can see that this is x3 of t is equal to, it is decomposed. Now look at this. Now let us find out the three set of equations. See, this is the first set, x1 of t is equal to x2 of t. This is the second equation, and this one is the third, right? Right. Now how many equations you have? Equations is 3, and the order of the system is 3. And how many variables? Variables will be x1 of t, x2 of t, and x3 of t. Okay, so state equation is nothing but it is the first order derivative of the state variables. So how many number of state variables you have, that much first order derivatives you will be having. Okay, it's clear. This is how. So from this we understood that this state equation is actually a function of the state variable as well as the input. Okay, now in the next session we are going to generalize a state equation. Okay, now look at this sets of equation which we have derived. Now from this you can convert this into a matrix equation of the form, say x1 of t star. Okay, now the second row will be x2 of t star and x3 of t star dot. It's not star, it is dot. Okay, this is equal to, okay, coming to the last equation, you can see that this is a combination of x1 of t, x2 of t, and x3 of t. So you can have a column matrix like this, x1 of t, x2 of t, and x3 of t, right? So this will be, as per the last row will be minus a0, right, minus a1, and minus a2. What about the next row? x2 of t, you have x3 of t only, so this is 1, this one is 0, this one is 0. What about the next one? In the next one it will be, you will be having only this as 1, 0, and 0, right? Now this is it. So this plus, and you can have a column matrix. You can see that in the first two equations there is no input, it is independent of the input, while in the third equation you have an input. So this is 0, 0, 1 into u of t. Okay, So this is actually the matrix representation of this, of the state equation of this third order system. Now I'm going to extend this to an nth order system. Now how to write the nth order system equation, or the state equation, okay. So now just have a comparison of the matrices which we have done already. So using that, you can have the generalized state equation, that is, it will be having, so what type of matrix this will be? So this is a 3 into 1 matrix. Look at this. This is going to be a 2 into 1 matrix. Why? Because there are only two state equations, so 2 into 1 matrix. So this must be a 3 into 1 matrix. So this must be an n into 1 matrix. So that means it will be having x1 of t dot, x2 of t dot, right, up to xn of t dot, right. So this is equal to you are going to have an big matrix. Now what is the speciality of this matrix? Okay, this matrix. So look at this. In this case you have a 2 by 2 matrix. In this case you have a 3 by 3 matrix. So it depends on the number of variables. So that means it has got a 3 by 3 matrix, meaning it is 3 variables, meaning this matrix is going to be a 3 by 3 matrix. So what I'm going to do is, so I'm going to represent as in the matrix form. I can represent this as A11, A12, A up to A1n, right? This will be A21, A22 up to A2n, and this will be AN1, okay, AN1, N2, and it goes on like this and reaches ANN. So that means this is an n by n matrix. Now n by n matrix into, this is a column matrix again with n rows, right, into 1. So this is an n into n matrix. This is an n x1, x2 up to xn are the state variables, or this is the state variable matrix, and just see whether this is the product. So it is conformable, right? This is how you need to test the conformity, and that will result in what is the result of this product. This is going to, the product is going to give you an n into 1 matrix. Okay, so this is an n into 1 matrix, this is an n into 1 matrix, and plus we can, now this must be this is bn, meaning this must be an n into 1 matrix, right? So overall, when n into 1 matrix multiplied by u of t is going to be another n into 1 matrix. Now if you have two n into 1 matrix, then you can add these together, so that you will get an nth order state equation. Okay, now in short, this nth order state equation can be represented by in the matrix form as a variable x dot. This is actually the derivative. X stands for the state space variable, state variable, while x dot represents the derivative of the state variable. This is equal to this matrix. This matrix is generally called as a capital A matrix into x, where x is the state variable. So this is the first derivative of the state variable. This is the state variable, right? Plus this is again a B matrix into U. Okay, where U is the input. Now you have matrix A and B. Now what is this matrix A and B called? Now A matrix, A refers to this A, actually A refers to the system. This one is called as a system matrix. This is called as a system matrix. Okay, system matrix, while B is called as the input matrix. Okay, so this is the input matrix and this is the system matrix. That means this matrix has got will give you the information about that system. This matrix gives you the information about that system, and along with that input you will be getting the state equations of that system. Okay, now this is just a part of the state model, and the next is to derive the output equation of a system. Okay, now the system description will be complete only by not only I mean only by finding out the output equation. Now how will you find out the output equation? Now looking at the output equation, we can see that the output equation, so look at this, you have p outputs, y1 to yp outputs. Now each output depends on the inputs as well as the state variables. So you can write the output as, say, y1 of t will be a weighted combination of the input, right? So this can be written as, so from this, since it is, so each output is going to be a function of this input set as well as the state space set, so that you can write this as, say, I'm calling this a C11 into U1 of t, right, plus C12 into U of 2 into U2 of t. Okay, so this is okay, this is a variable, so this is the, okay, now output equation, we can see that from the figure the output equation is the function of these two variables. So that is the sum of the weighted sum of this input as well as the state variables. So you can write this y1 of t as equal to c11 into x1 of t plus c12 into x2 of t, etc., up to c1n into plus then you have a d, right, then you have, say, some d11 into, okay, so then you have some d11 into, this is d11 into u1 of t plus d12 into u2 of t, etc., up to d1m of of t. Okay, now similarly you can write equations till yp of t. So this will be c11 of x1 of t, it's not c11, cp1, cp2, up to cpn of xn of t plus dp1 u1 of t up to dpm of t, right? So from this you can have a general expression like this, say a matrix y1 of t, y2 of t, etc., up to yp of t, which results in the p into 1 matrix. This is equal to a c11 up to, this is going to be an x1 x2 up to, okay, you have n columns and p, so this is going to be a p into n matrix starting from say c11, c12 up to c1n, and you have cp1, cp2 up to cpn. So this is a p into n matrix into how many variables? N variables, x1, x2 up to xn, right? Plus you have the inputs, okay, d11 up to d1m. Okay, so this will be into so this will be d11, d12 up to d1m, into u1 of t up to um of t, right? Okay, so what type of this thing will be? This thing will be P into M matrix. This is a P into M matrix, while this one is an M into 1 matrix. So this is again multipliable, resulting in a P into 1 matrix. This is P into N, and this is an N into 1 matrix. So this is again multiplied, resulting in a P into 1. So 2P into 1 can be added together. So you can finally arrive at a matrix equation as the output equation Y matrix is equal to, this is called as a C matrix into X. C, or you can write like this as well. So Y is equal to C into X plus D, capital D into U. This is the output equation. Okay, so this is the output. This is called as the output equation, and this matrix C is called as the output matrix. This is called as the output matrix, or this matrix gives you an idea about how the output to be. So this actually determines the output, while D is called as the coupling matrix. D is called as the coupling matrix. Okay, so it represents the direct coupling between the input and the output. So that's why this D matrix is called as a coupling matrix. Okay, so these two set of equations, that is x dot, the equation x dot is equal to ax plus bu, and y is equal to cx plus du, forms the state model of a system. Okay, hope you understood.